So now we'll talk about the second derivative test. It's an extension of the first derivative test. So notice that the first step in the second derivative test is, again, to just find the critical values like we did in the first derivative test, but this time we have this nice shortcut. Instead of making a sign chart for f prime like we did in the first derivative test, now we can just plug in each of the critical values that we find into f double prime, and if f double prime gives us a positive value at that critical value, then we know that we're looking at a picture that's concave up. And if f double prime is negative, then we're looking at a picture that's concave down, and that's actually enough for us to tell whether we're sitting at a local max or a local min. So here the goal is very similar to the goal in the first derivative test, but this time we can just use the second derivative to figure out whether we're sitting at a local max or a local min. Okay, so let's look at some examples of this. In 7 it says consider this function, and we want to find all of the local extrema using the second derivative test. So I'm just going to go through this step by step. The first step is just to identify any of the critical points. So to do that, we're going to take the first derivative. So if I take the first derivative of this function, I would get a negative 15x to the fourth plus a 15x squared. And if we're on the hunt for critical points, then what we should do is we should set this equal to 0. But it'll be a little bit better to factor it first. It'll be a little easier to see where these zeros lie. So notice that these two terms have a common factor. I could factor out either a plus or a minus 15x squared. If the first term is negative, I tend to like factoring out a negative from both terms. So I'm just going to factor out a negative 15x squared. It would also be fine to just factor out a positive 15x squared. But this is what's left over whenever we factor out a negative 15x squared. And notice that this further factors as a negative 15x squared times x minus 1 times x plus 1, because x squared minus 1 is a difference of squares. So this is f prime. And now that this is fully factored, it's easy to see that there are only 3 critical points. Remember, the critical points are the places where f prime would be 0, but in order for f prime to equal 0, either this first factor would have to equal 0, which would mean x equals 0, or the second factor would equal 0, which means x equals 1, or the third factor would equal 0, which means x equals negative 1. So those are the critical points for this particular function. And now what we need to do is we need to decide whether those critical points are local maxes, local mins, or neither. And if we were proceeding by the first derivative test, what we would do is we would plot those on a number line, like that, and then we would pick a point in each of these intervals to plug into the first derivative, and we would decide what the signs are for the first derivative. And then we're looking for sign changes from positive to negative or negative to positive. But thankfully, we don't have to do that for all of these points. Instead, what we can do is we can take these 3 critical points and we can plug them into the second derivative to just determine what the concavity looks like at each of those points. Now, in order to do that, we need to actually compute the second derivative. So we're just going to take another derivative. So we'll take a derivative of this function. If I take a derivative of negative 15x to the fourth, that would give me negative 60x cubed. And then if I take a derivative of the next term, 15x squared, what I would get is a plus 30x. So that's the second derivative of f. And now we're going to plug in each of the critical points that we found into the second derivative to determine the concavity. So if I plug in 0 into f double prime, I would get a 0 plus 0, which is 0. If I plug in 1, what I would get is a negative 60 plus 30, which is a negative 30. We don't actually really care about the value here, we just care that it is negative, so it's smaller than 0. And similarly, whenever I plug in negative 1, what I would get is a positive 60 minus a 30, and that will give me a positive number at the end. So because that didn't get any cleaner. There we go. Okay, so because the concavity for this first critical point is, or sorry, for this critical point is negative, what that means is that the picture looks like this near this critical point 1. So because we have a negative concavity or a downward concavity near 1, we know that 1 is going to represent a local max. And similarly here, we have a positive concavity near this critical point, and that means that near -1, we're looking at a local min, because here we have a positive concavity and a critical point inside. So we know that 1 is a local max and -1 is a local min. Unfortunately, we don't have any information about what well, we do have information about the concavity, but we don't know whether f double prime at 0 is going to give us a local max or a local min, because this is neither positive nor negative. So unfortunately, this is just inconclusive. So one downside to the second derivative test is that sometimes if you just get a 0, you don't know if you're looking at a local max, a local min, or neither. So when that happens, what we have to do is we have to fall back on the first derivative test, but we only have to do that for this point at 0. So I will, just to make the video a little bit shorter, what I'll do is I'll just skip a step, and I'll promise you that if you plug in a point over here into the first derivative, you'll get something positive. And if you plug in a point over here into the first derivative, you'll again get something positive. So notice that the first derivative doesn't actually change signs at 0. And what that means is that the first derivative test says that 0 is neither a local max nor a local min. So we can actually throw out 0 as a candidate for the local maxes or local mins. But we did need to check that 0 was neither a local max or a local min, because this second derivative test was inconclusive at 0. But fortunately, it was conclusive for these other 2 points. What we get is a local max at x equals 1 and a local min at x equals -1. And those are the local extrema for that function. So we'll do something similar in this problem. So we're looking for the local extrema of this function, f of x. And we'll go through the same procedure. So if you'd like, you can compute both the first and the second derivatives right away, but I'm just going to follow the procedure that's in your notes above. So I'm just going to first focus on finding the critical points. So we'll compute the first derivative of f. If you take a derivative of the first term here, that would be an 8 times the derivative of e to the x, but the derivative of e to the x is just e to the x. So that first term is still going to be 8e to the x. Now if we take a derivative of the second term, what we'll get is the same exponential, so it'll still be an e to the 2x, times the derivative of that upper part, or times the derivative of the exponent. The derivative of the exponent is a 2. So this is f prime. And again, when you're looking for critical points, it's a good idea to factor out any common factors that you see here. So I noticed that 2e to the x is a common factor between these. So I'll go ahead and factor out a 2e to the x from f prime. Notice I'm not taking a derivative here, I'm just rewriting f prime. If you factor out 2e to the x from the first from the first term, what you'll get is 4. And then if you divide the second term by 2e to the x, what you'd be left with is just an e to the x, rather a negative e to the x. So now if we're looking for critical points, we want to know when this thing is equal to 0. So we would set 2e to the x times 4 minus e to the x equal to 0. You just set the first derivative equal to 0, and then you solve that equation. Now here we have a product of two things. We have 2e to the x times this thing, and that's supposed to equal 0. But exponentials themselves are never 0. So this circled term, or this circled factor, is never going to be 0. And therefore, if this product is 0, what we get is that the second factor here has to be 0. So because that first factor is non-zero, we get 4 minus e to the x equals 0. And now we can solve this equation for x. So if I just add e to the x to both sides, I get 4 is equal to e to the x. And then taking the natural log on both sides, I'll get ln of 4 is equal to, is equal to x. So this is our only critical point. And it's okay that we only have one critical point. We're still going to take this and try to determine whether it's a local max, a local min, or neither. And for that, we'll again use the second derivative test. To compute the second derivative, I'm just going to take a derivative of the first derivative. So again, if you take the derivative of that first term, it'll stay the same. The derivative of 8e to the x is just 8e to the x. And if we take a derivative of that second term in f prime, we'll get a negative 4e to the 2x. Because we're again just going to be multiplying what we have originally by a factor of 2, since that's the derivative of the exponent up there. And now we don't actually care about finding the zeros for f double prime. All that we need to do is take this critical point that we found a second ago and plug it into f double prime. So I want to know what is f double prime at ln of 4. And if that's positive, then that means that we're looking at a critical point where the concavity is upward. And if this ends up being negative, then that means we're looking at a critical point where the concavity is downward. And that would be enough for us to decide whether we're looking at a local max or a local min. So here I'm just going to plug in ln of 4 instead of x. So this would be 8e to the ln 4 minus 4 times e to the 2 times ln 4. And this is something that you could plug into your calculator, but just to remind you some rules for resolving these exponential terms, I think it'll be good for us to just talk about some of these rules. So e to the ln 4 is actually cancellative because e to the x and ln of x are inverse functions. So these would cancel and just leave you with an 8 times 4 in that first term. Simplifying the second term is similar, but things are a little bit trickier. We can't just cancel the e and the ln because there's this 2 in the way. But what we can do is we could rewrite this term as an e to the ln of 4 quantity squared, because whenever we have repeated exponentiation, that's the same thing as multiplying the exponents like we're doing up here. And now that we've rewritten it, we can do this cancellation because on the inside of the parentheses, we have an e to the ln of something. So this would end up being an 8 times 4 minus a 4 times a 4 squared. And this ends up being 256, I think. You can just trust me on that one. But in particular, this is a positive number. And because this is a positive number, wait, is this right? This is not right. So actually, this ends up being, sorry about that, this ends up being a 32 minus a 64, which is actually a negative number. So because this is negative, what that means is that if you're looking at the original function f, and you're looking at its critical point, ln of 4, we know that the concavity near that critical point is going to be negative, so this picture is going to be concave down. And that means that near the critical point, the picture looks like this. And therefore, the second derivative test says that you're looking at a local max. So ln of 4 is a local max. Okay, so now we've found the local maximum for the function. Lastly, let's look at this example 9, and then we will work on the other examples in the next video. So in example 9, things are a little bit nicer. We're not actually trying to find all of the maxes or mins or anything. We just want to know, is the graph of G concave up or concave down at this particular point? And if we want to know about the concavity, all that we need to do is figure out whether G double prime is positive or negative at that point. So to figure that out, I'm just going to compute G prime and G double prime, and then we can plug in x equals 2 into g double prime. So this might be a good example for you to just pause the video on and then work through on your own, but it's also fine if you just want to hang out and watch me do it. So if you compute g prime, we would be using the power rule on each of these terms. So that would give us a 3 times 3, which is 27. No, it is not. Sorry about that. So 3 times 3 will give us a 9x squared, and then we'll have a negative 3x squared. The derivative of that will be a negative 6x, and then the derivative of that third term will be a negative 4, and the derivative of the last term will just be 0. So this is g prime, but we're not done because we're looking for concavity, so we want to compute g double prime. If I take a derivative of g prime, then what I'll get is an 18x minus 6. And now if I wanted to know whether this function g was concave up or concave down at this particular point, I just need to take g double prime and plug in that point. So I would evaluate this function up here at 2, and that would give me an 18 times 2 minus 6. Now you don't have to actually finish computing this. It's clear that this is a positive value, because 18 times 2 is clearly bigger than 6. So it's fine with me if you just stop here and say that the answer is concave up. In other words, g is concave up at the point x equals 2. Okay, and in our next video, we'll talk about the point of diminishing returns, which is